Hi there, this is a quick video introducing chapter 12 topic, which is gases. Mostly this first video just going over vocab, some of it's review, some of it's new, some of it's kind of a combination of both. First thing, solids, liquids, and gases, we've talked about these before. If you remember the term fixed means it does not change very easily. So solids don't change shape or volume very easily. Liquids can change shape very easily, so they're variable shape. The volume doesn't change. But gases, the focus of this chapter, the shape and the volume of gases can change very easily. So we say variable shape, variable volume. A lot of these terms I'll just let you go over. One thing I want to highlight is the kinetic molecular theory of gases. It's very important for this unit. Basically, it's a theory that gases are made up of molecules, and those molecules are in constant, rapid, random, straight line motion. So the room you're sitting in right now is full of air, which is a mixture of gases, and that air is made up of little molecules of nitrogen and oxygen, carbon dioxide, and maybe some methane, maybe some argon, all that stuff. And those molecules are flying around the room in constant motion, so they're nonstop. They're moving very quickly. It's the rapid part. They're moving in every direction. It's not like they're all going that way. So the direction is random, and they're all going in straight lines. They go in straight lines until they hit something. When they hit something, like you or the wall or the phone in your hand or whatever, they bounce off that and they go off in a straight line in a different direction until they hit something else. The three terms that we'll be using, or three variables that we'll be using quite a bit through this unit, are temperature, pressure, and volume. Temperature, we've defined temperature half a dozen times already. It's, again, a measurement of the motion of the particles. Volume is how much space something occupies, or how much space it takes up. And pressure, which we haven't talked about, is force per unit area. Now, those gas molecules that are flying around the room you're in right now are hitting you, and they're hitting the walls and everything in the room. And when they hit something, they exert a force. And if we measure that force for a certain amount of area, that's what we refer to as pressure. Atmospheric pressure is the pressure of our atmosphere pushing down on us. I think the best way to understand atmospheric pressure is to think about if you were at the bottom of the ocean. If you were at the bottom of the ocean, the deepest spot in the ocean, you would get crushed. You would get crushed from all the weight of all that water above you. You know, thousands of feet of water pushing down on you has a lot of weight. It would literally crush you. On the surface of the Earth, we have a thick atmosphere to our planet, and that also has weight. Now, it's not going to have as much weight as all the water at the deepest spot in the ocean because water is much more dense. Our atmosphere isn't very dense compared to water, but it still has weight and it still exerts a pressure on us. And you'll get to see some examples of how atmospheric pressure works, basically, on the demo day. Barometer is a device used to measure atmospheric pressure. You may have heard weather people talk about, you know, the barometer is rising, barometer is falling. Atmospheric pressure and different weather systems affect the atmospheric pressure. Vapor pressure is created by the vapor above a liquid. Now, if I have a glass of water, at the surface of that water, some of those H2O molecules are breaking away from the liquid state and they are becoming gaseous H2O. Now, those gases, or that vapor, the gaseous H2O molecules, they create a pressure. And that pressure gets exerted back onto the surface of the water. So again, we have a liquid. That liquid is evaporating. And those evaporated molecules of that liquid create pressure. And that pressure created from those molecules is what we call vapor pressure. Now, this is important because it's related to boiling. The boiling point, we usually think of the boiling point as a function of temperature. We heat up water, it starts to boil at 100 degrees Celsius or thereabouts, and that's the boiling point of water. It's also pressure dependent. And again, you'll see a demonstration of this on the demo day, where I will boil water at room temperature. So it's both pressure and temperature dependent. Basically, what we do when we heat up water is we increase the vapor pressure, because as the water gets hotter and hotter, it evaporates faster and faster. More and more particles hang out above the surface of that water, and they create more and more vapor pressure. Now, once that vapor pressure gets up to the point where it's equal to the atmospheric pressure, the pressure around it, the water will boil. And again, you'll see me boil water at room temperature without heating it at all, just by lowering the pressure around the glass of water. The rest of this, I'll just let you look at. STP, there are a few questions in the practice quizzes that refer to standard temperature or standard pressure. It's just another way of saying 0 degrees Celsius or 1 atmosphere. 1 atmosphere is a unit of pressure, and 1 atmosphere is basically the atmospheric pressure on a normal day at sea level. So there are some questions that refer to STP, or they might just say standard temperature, which is just a fancy way of saying 0 degrees Celsius, or standard pressure, which is again just a fancy way of saying 1 atmosphere. Molar volume of gas, if we have 1 mole of gas at STP, it will take up 22.41 liters of space. You may remember that number from doing STOIC back first semester. Avogadro's law, you may remember Avogadro's name from Avogadro's number. The work Avogadro actually did had to do with gases, and he figured out that equal volumes of gases at the same temperature and pressure will have the same number of moles, or the same number of atoms in that. Like we've had 2 balloons, they're the same volume, same temperature, same pressure. It actually doesn't matter if they're different gases. They will have the same number of molecules in either balloon. We will also be doing some conversions. These will be given to you, but just a reminder that how to convert liters between milliliters and temperatures between Celsius and Kelvin. So that's it for this video. The next video will be a short one on how to do pressure conversions, and then there'll be a couple of gas law videos. If you have any questions, stop in and see me.